STEM Hub. Engineering concepts made simple.
So here we are looking at free damped vibration for a viscous damping. So freely damped, so it's moving freely, it's not forced. There's no forcing force that is moving the damper to move. You know, we have our K, then we have our C. These are spring stiffness and these are damping coefficient. So it is freely damped, it is moving, but it is not forced by an external force. So a vibrating system is defined by the following parameters. We have our mass, we have our K, we have our C, which is K is a stiffness coefficient, damping coefficient, and we have our damping factor. That's what we are to get. We are to get a natural frequency of the damped vibration, the logarithmic decrement, and the ratio of two consecutive amplitudes. So, and we're also to get the number of cycles after which the original amplitude is reduced by 20%. This question iterates that x2 would be 0.2 in terms of the reduction of x1. I hope that is obtained. So as we move, we'll see it. So these are damping coefficients, critical damping coefficient, CC. We have it to be, the standard formula is 2 square root of mk. Now, our m is our mass, our k is our spring stiffness. We get our critical damping coefficient. Now, our damping factor is C over CC, C which we already been given in the question, over CC. This gives us our damping factor. So, we have underdamped, damped, and overdamped. So, when your damping factor equals 1, we have a totally damped system. Then when you have this factor greater than 1, we have an overdamped system. So since this is less than 1, this system is underdamped. So as we said before, that I want to get a natural frequency of the damped coefficient, which is the omega d. So we get a natural frequency, which we are going to get from square root of K over M, standard equation, then 1 minus our damping factor that we obtained before. So we have Wn equals to square root of K over M. Our K is 100, our mass is 3. We get our natural frequency in rads per seconds. Then our damped natural frequency is Wn over 1 minus the damping factor. We have this to be 5.75. Now, we now want to get the frequency itself. Fd equals to omega d over 2 pi. Because we know that our omega is 2 pi f. So from this, we have our value to be 0.916 arcs. So this 0.916 arcs is our damped frequency. Then we want to get our decrement, our logarithmic decrement. So now to get our logarithmic decrement, our formula is 2 pi. Our damping factor all over 1 minus damping factor square. These are standard equations that were proven from a set of other differential equations. Now we have 2 pi times 0.0866, which we obtained previously. Upon analysis, we have this to be 0.5462. So this is our logarithmic decrement. Now, as we explained before, our logarithmic decrement. Now I want to get a ratio of two successive amplitudes. Now, which is x1 over x2. That's what we want to get. But you know that our formula for logarithmic decrement is ln x1 over x2. So I apply exponent to both sides. I get this. Then ln of this cuts out ln x1 over x2. Exponent of 0.5462 as we initially got gives us 1.7267. So now, as we initially said that it reduces by 20%, like the first one will be 20% of the previous one. So meaning that xn plus 1, so if this is x1, this will be xn plus 1 is 0.2 of the previous one. So if we have like 10 in terms of the amplitude before, this would reduce, this will be 2, the next one that we're moving to. So I know that this is a logarithmic decrement 1 over n ln x1 over xn plus 1. Now this equation sums up series of logarithmic decrement, series of systems as we move. So we have so this is trying to tell us that, okay, we want to know how many amount of movements we have to move, how many amount of cycles we have to move to achieve this. So the next one will be 0.2 of x1, but how many cycles do we have to move to obtain 0.2% of the initial x1? So we have this. This is talking about the summation of different cycles that we are going to have. So we know this xn plus 1, which is that particular amplitude that gives us, that make us achieve that. So we have x1 over 0.2 x1 ln 1 over n. So this n is the amount of cycles that we want to get. So if upon analysis we obtain this to be 3 cycles, meaning that we have to move 3 times to be able to get this change in amplitude. So in the previous video, we're going to look at a vehicle question, whereby we're going to look at this vehicle moving, whereby it has a spring and also a damper, and it is being displaced in the positive direction of x.